Hi everybody, hope you are doing fine. Let us resume our discussion on the expanding universe model. And we are particularly talking about one model, which is said is the Big Bang model, where the density of the matter changes with time. So that is what the Big Bang model is. Now let me remind you of a few things that we have already discussed. We started with a metric, which is the effort W metric, and from that we saw that, or we just stated that the universe has different types of components. So we call those components like the radiation, which is here, like the matter, which is here, and there is something we call this a cosmological constant, which is here. And these components grow with time or change with time or with scale factor differently. For example, the density of the radiation changes as a to the minus 4. The density of matter changes as a to the minus 3. And the constant component obviously doesn't change with time. Using these, we figured out that we can write the Hubble constant, which we will call now Hubble parameter, as a function of A, like this, which is related to the Hubble constant, and these parameters of the matter densities in this particular way. So these omegas are called the omega parameters or density parameters of the universe. How are they defined? There, so omega matter naught, for example, is the ratio of the matter density at present compared to the critical density at present. And remember, the critical density is the density for which the universe will be, the spatial part of the universe will be flat, which is what will give you the metric or the effort WL metric that we talked about. So this is the definition of the critical density. And different parts comes at different numbers. So omega matter at present is 0.3, omega lambda at present is 0.7. I asked you to look at what is omega radiation at present. You should have a look at it. I have not filled up that value. And you can see that this is 0.3 and 0.7. This must be very, very small. The scale factor and the redshift. Remember, redshift is the observable. Scale factor comes from your theory. And they are related by this expression. And we have assumed that at present A is 1, present means t equals to t0, A is 1, and the redshift is obviously 0. So these are the last set of things that we have learned, and we said again and again that these are very, very fundamental to the modern cosmology. The slide you are looking at right now is the most fundamental to modern cosmology. So we'll just start from there. And we'll try to understand what happens to the different parts of the universe or different components of the universe. And we'll start by radiation. So remember, for radiation, we call it rho gamma. The density of radiation is called rho gamma. And we said we have not proven, we have just given a heuristic argument for it, but that's all right for this course. This goes like this, right? So let us look at our universe, which has only radiation. This is just for academic purpose. We'll try to understand what happens if the universe is filled up with different parts, different components only. So we talk about only radiation, so we call it radiation dominated universe. Now it turns out that in the history of the universe, there was a time where the universe was radiation dominated, and this actually serves as a rough solution of things for the universe during that epoch. if we want to do justice to the modern cosmology, where we can calculate things up to very high precision, you should use all the components together. But anyway, for the time being, let us see what happens in a radiation dominated universe, which essentially means that all the universe is radiation. So omega, so this essentially means that omega is gamma. So say for the present time is 1. Okay. So all the matter there is only radiation. So it's all omega, entire omega is in omega gamma. So what happens for such a universe? So obviously this universe, we do not belong to this universe. We are not radiation, but just for an academic purpose, we can see what happens. So you see that we start with that fundamental equation a dot by a, which is h square of that. And for the radiation dominated case, it is proportional to minus a to the minus 4. And you see h naught is essentially 1. Sorry, omega gamma naught is essentially 1. I can write it roughly as h naught square a to the minus 4. It doesn't make much meaning because this h naught is obviously not the h naught that we can measure, because we don't live in a radiation dominated universe at present. But it's all right. You can put in any constant over h in place of h naught over here, and we will do that shortly. Okay, so let us work it out now. So to work out, we will just do a few steps. So let me do that here. So a dot square becomes h naught square a to the minus 2. Once I bring that a to the minus 2 from there to there, it becomes a to the plus 2. And then I can do one more step where I get this. I can bring in this side now and take the square root. So I get a dot equals h naught. Or I can go one more step, write this as dA dt. So d I keep here and the dt I put in this side. Now I can do an integral. So all these things boils down to, in the left hand side I get a square by 2. In the right hand side I get h naught t, and I can choose my at t equals to 0. We don't understand what it is yet, but let's say that at t equals to 0 equals to 0. We don't understand what that either, but if we choose that, we get a equals root over of h naught by 2 t to the power half. So all this may not be quite meaningful. This constants etc. may not be quite meaningful, but what right now we are looking at is the case for the radiation dominated universe, where we can definitely say one thing, that AT grows as t to the power half. So that is the main result that we get out of this calculation for the universe which only has radiation. So for a radiation dominated universe. Okay, now I will not go through the matter dominated and the cosmological constant dominated universe. So for the matter dominated universe, you have to use a to the minus 3, and for the cosmological constant dominated universe, it is a to the 0, or constant. Right now we have just used a to the minus 4 for the density. So if we use this, we can fill up a table. So the table is type of universe. How does rho changes as a function of A, and how T changes A changes as a function of t. So if I want to fill up this table, so let me so this is the table that I want to fill up. If I want to fill up this table, so first I come with radiation dominated, and this we know that it goes as a to the minus 4. And with respect to a, we just have calculated, with respect to t, a goes as t to the half. If I do the same thing for the matter dominated, this we know a to the minus 3, and this is your homework to work out that this will be t to the 2 by 3. And once you come to cosmological constant dominated, this goes as constant, or I can write a to the 0, and this will go as e to the t. And obviously there will be divided by some time scale, but let me not be so much critical here. So this is the table that we get. Okay. So for different time in the universe, the rho and a changes differently. So let us try to plot this. So let me plot here first. Log of a versus log of rho. Why do I do that? Well, if you look at these relations, they're all power law relations. Means that I can write them as rho, any rho, a is some constant times a to the power some number alpha. So that alpha can be minus 4, minus 3, or 0. So if I take ln of rho, then that becomes ln of c plus alpha times ln of a. So you see, if I plot between ln of rho as y, and if I have ln of a as x, so this is essentially this looking like a line y equals mx plus c. So it looks like a log plot, it looks like a straight line. And how will these look? Well, the first one comes with minus 4, means that it will. Okay, so first of all, you realize that we are plotting ln of a is 0 somewhere else, somewhere here, right? So that's present. This is present. Because a equals to 1 at present, ln of a is somewhere here at present. Now, we know the matter, we can claim that we know these densities at present because that is what these numbers tells you. So these numbers tells you the values of the densities at present. You see, you may say that, well, these numbers has a rho critical knot also, but the rho critical knot involves the only thing that comes from cosmology is h naught square, and the h naught square we already know the value. Hubble measured it long back. So we know these numbers at present. We know the rho radiation knot, rho matter knot, and rho lambda knot. And these values will be somewhere in this dashed line. So when I try to plot, I realize that the first one has minus 4 slope. So I plot it such that it has a minus 4 slope, and this much is rho gamma naught. So this is rho gamma. It has a slope of minus 4. Well, that is very less, right? At present, that is very less. So this will be the lowest amongst all the things that we are plotting. The next thing is the raw matter, which will be something like, maybe something look like this, and this will corresponds to rho matter naught. All right. And the next thing will be rho lambda, and that's a constant, and that has the highest value, so it will correspond to something like that, right? So what happens here? You realize that now if I look at a part of the universe, and let me highlight that part for you with a particular color. So if I look at this part of the universe, sorry, if I look at this part of the universe, this part of the universe is truly, the radiation is maximum, the rho lambda is maximum compared to the others. Remember, this is in the log scale, so the others are really small in this part of the universe. So this is your radiation dominated universe. On the other hand, here, so let me draw it with a different color. This region of the universe is cosmological constant dominated, because I'm sorry, so this is again shaded the region wrongly, so let me go back. So here the cosmological constants start to dominate, so this is the region where the universe is cosmological constant dominated, because you see this, the line corresponds to the rho lambda is highest in this region. And then I have another region where the universe in between the region is matter dominated, right? So this is the matter dominated universe. This is the cosmological constant dominated universe, and this is the radiation dominated universe, right? So you realize that though we looked at these different types of regions of the universe separately, but this analysis directly tells us that the universe was dominated by different parts at different times. In fact, if I follow the trajectory, initially the universe was radiation dominated, then it became matter dominated, and then eventually, right now, it is cosmological constant dominated. So that's why omega lambda is 0.7, omega matter is 0.3, and right now, omega radiation is 0, almost 0. Well, it's actually 10 to the minus 5, but it's very small compared to 1, so you can consider it to be 0. So this is the history of the universe. Now you realize one more thing here. I have the present, but I don't have what is the past. Where is there so this I am plotting with respect to A. Is there a equals to 0 in this plot? Now to look at that, I need to see this part of the table where I have the A dependencies. And again I do the same trick. I plot things with respect to log of with respect to the log axis instead of directly plotting the functions. Now I have the two power laws here, but I also have an exponential. And let's first check what happens to an exponential if I take log. So I have rho, or in this case it's not rho, I'm sorry. I have a of t goes as, say, some c times e to the t by some t lambda. Okay, so if I take ln of a here, I take ln of c, and this just becomes t by t lambda. So it doesn't become log of t by t lambda, but it goes to t by t lambda. So it looks like exponential. So if I plot ln of a over versus ln of t, this will rather look exponential. But that's all right. So let us try to do that plot. and see. And we don't even need to plot the present day because we are really trying to understand the past. So let us just plot the two cases of radiation and matter. And how will they look like? Well, you see, in these cases, if I consider that there is a t equals to 0, then a becomes 0 at that. Right? So that's how you have got, say, for example, the case of radiation dominated. We took t equals to 0 at a equals to 0. So that's an assumption that we get t equals to 0 at a equals to 0. So, nevertheless, let us try to see what happens. So I will use these colors for, so it's matter dominated. Matter dominated, use red. The matter dominated has a higher slope, so this will look like this. And the radiation dominated has a lower slope, so it will look like that, right? So this is gamma and this is matter. Okay. So with our assumption, both of them goes to 0 at t equals to 0. And we see that if we consider the fact that we have already realized that the universe was radiation dominated at the beginning here. So this is the thing that the universe will follow at t equals to 0, at least t near to 0, at least for the time being. So what happens to the universe when it becomes near to t equals to 0? Near to t equals 0, what happens? So let us ask that question. So we see that near to t equals to 0, which is this regime, the density becomes very large. So this is a log scale, right? So the density becomes very, very large. It becomes larger as a to the minus 4. So you can, if you make a 1/2, so if as I am going this side, there is reducing. So if I make, say, a 1/10, then the density increases by 10 to the 4 times. Soon there will be a density where soon there will be a density. The density will be extremely, extremely large at that stage. Also, we see that as that happens, as a decreases, t also decreases. This plot is showing you that as a decreases, which happens in the previous plot, t also decreases. Well, that's what we mean by the expansion of the universe we said earlier, but that we see explicitly from these plots now. So what happens to the proper length? That also has to decrease, because you remember that the proper length is a times the comoving length or comoving distance. So which means that now the proper distance also decreases. So there will be a time in the universe, in the past in the universe, that this proper distance is extremely, extremely small. How small? It's at the atomic scale or even smaller. So let me now write down something that most of the popular videos about the Big Bang theory doesn't understand and states the theory wrongly. So let me write down this at this point of the discussion. It is clear that there was a time in the early universe when the proper distance between 2 points having unit co-moving distance. So this unit, what I call unit, is not very important here, because you see that if I call it 1 meter, for it to become smaller than 1 millimeter will take a certain time in the universe. If I call it 1 kilometer, it will take a different time in the universe, but it will always happen to such a expanding universe. So this was very low. Sorry, very low at the atomic scales. And I don't need to even go even smaller, because you see, at the atomic scales, all the classical theory, classical means not quantum, all the classical theories at the atomic scale fails. So do our expanding universe model. What does it mean? It means that in these plots, when I am reducing the time, there is a time, certain time, which corresponds to when this becomes, the quantum theory becomes important, and this region, this theory doesn't work. Here there is this time, in this region, this theory doesn't work. And you cannot say what happens to the universe sufficiently long ago just because of this. What is the consequence of this? The consequence is, if you have come through my discussion till now, I have never talked about a Big Bang. I've talked about a Big Bang model. I've never talked about that the universe started with a Big Bang, because the start of the universe corresponds to that t equals to 0, and the present theory of the universe cannot extrapolate it up to t equals to 0. We don't know what happened earlier than a certain time in the universe. There is no theory of the universe that can predict it at this point. Well, there are theories which will push back that time to earlier and earlier time. Like, for example, there is a theory called Inflationary Theory, which is a part of this expanding universe model, but it will evoke a different type of matter at an earlier stage than the radiation dominated universe, which will solve certain problems which we'll not discuss. But anyway, so that will just push the time back to an earlier time. You can never talk about that t equals to 0, which we discussed here. So this we never know. Okay, unless, okay, so we never know this, but sometimes just to do integrals, etc., we'll use t starting from t equals to 0, and that became the source of all confusions. All those integrals that we'll talk about shortly just have academic purposes. They does have physical meanings, but they doesn't mean that you are actually wanting to do it from t equals to 0. You are always doing it from t equals to 0 plus some epsilon. Okay, so this is a very, very strong statement, and this you should remember out of this cosmology part of the course, and you should never say in public that from now on that the universe started with a Big Bang. So that gives a wrong message. Sometimes scientists say it doesn't mean an explosion, and you can look at places in the internet to see how this theory came about, how the name came about of the theory. why it is called a Big Bang theory. But anyway, so I'll not go into that story. Fine. So if you have come up to this, so then let us go to some more interesting discussions. Okay. So first question that we can ask is, and again, so in the following discussions, often we'll choose to do integrations from t equals to 0. And let me remind you again that it doesn't mean, when you do integrations from t equals to 0, it doesn't mean that we are actually doing it from t equals to 0. We may be doing it from t equals to 0 plus some epsilon. And the result actually doesn't matter if we choose that epsilon properly. Sometimes it does, but okay, so I'm not going to those intricacies right now. Let's ask the question now. If we choose t equals to 0, then what is the age of the universe? Okay. So how do I get to that? Before I get to that, let me show you some simplifications of what we have already done. So we have written down this, that h of a squared equals h naught squared, and then I have this omega gamma naught a to the minus 4 plus omega matter naught a to the minus 3 plus omega lambda naught to the power this one. This I can all this is often always written as h of a equals h naught, and the square root of this entire thing is written as e a. So this is essentially e a squared. Okay. So this is a shorthand of the same expression which is written there. I will see that this shorthand is useful. EA is dimensionless, as you can guess, and this shorthand is very useful. And I can write with abuse of notation again. I can write a corresponding expression like this, where Ez is nothing but the same thing, but A is replaced with 1 plus Z. So a to the minus 4 will be 1 plus Z to the power plus 4, like that. So I request you to look at this or derive this expression from this expression. Okay, derive the Z expression from the A expression. The reason ones like to write it down in terms of Z is because it is Z that we observe. We don't observe the scale factor. So we observe redshifts are Z. And just to remind you, h of A is nothing but A dot by A. Okay, so these are the machineries that we'll be using shortly. So what is this expression telling us? This expression is telling us that A dot by A is nothing but h naught times E. I can modify it a little bit. I can write this as, so A dot is dA dt, so I write dA by A EA 1 by h naught, that equals dt. Right? dA by dt is A dot and divided by A, and then I have just put these things in the denominator in the first term. If I choose to do this integral from t equals to 0, that's where the assumption goes, to the present time t0, then the present time is nothing but the age of the universe, right? So this I call the t age. If the universe started from t equals to 0, again I am saying that's an assumption, then at present I can say the age of the universe is T age, which is the result of this integral. So that is T age. What is that equals to? Well, I have 1 by h naught and I have this integral dA A E A. What is that integral over? Well, at all models at t equals to 0, A is 0 and at present A is 1. So that is the integral. It's not necessary that this integral converges. If this integral does not converge, then obviously the age of the universe is infinite. On the other hand, if this integral converges, then the age of the universe is finite. And you can see this entire integral is dimensionless. So 1 by h naught is order of the age of the universe. If now, okay, so let me give you a secret. When Hubble measured the value of h naught, it was around 200 km per second per megaparsec. At present, the value is around 67. So you see, irrespective of what model you choose of the universe, the model you choose of the universe is in this EA. That's the model of the universe. Which is irrespective of what model you choose, what are the values of those omega parameters, if you just change the value of h naught, the age of the universe will change. And the age of the universe at present is around 13.7 billion years. So to calculate that, you have to put the value of h naught and the omega naughts, which is over inside this EA, and do the integral and find out. So that I leave you as an exercise to figure out what is the age of the universe. Okay, so this, you see, immediately I get an expression for the age of the universe. Next, let us ask the question, proper distance of proper distance. So proper distance this we have actually done before, but now we will be doing it more carefully. Between emission and receive of light rays at 2 points time. Okay, so what is, so I have, remember that we did this when you when you try to explain Hubble's law. So I have this, so this I am drawing in the co-moving frame. So I have one point R1, the other point R2. They stand still, so these are their world lines. The vertical lines are their world lines. And at t equals to t1, there is a light ray emitted from it, and it's being collected at t equals to t2 there. So what is the proper distance between these two? Well, and that for the light ray, radial light rays, so this is radial light ray. For radial light rays, we know that dr is equals ADR is equals CDT. dr is the co-moving distance. So let me first calculate the co-moving distance. The co-moving distance is C integral of dt by A as a function of t. Right? And if I want to calculate the proper distance, what all I have to do is to multiply that with dt. So this is co-moving, this is proper. And these are by definitions, we cannot ask why they are so. And this light is passing from the time we said is t1 to t2, so the integral is over t1 to t2. Right? So let us look at this integral a little bit and try to recast it in a different form. And this will be very useful for us again and again. So let's do that. So we're looking at this integral t1 to t2 dt by dt. So what I do is, say, remember, when actually you have to calculate the proper distance, you can measure redshifts. You cannot measure time or a. That's the cosmological time you cannot measure. Why you cannot measure? Well, if you are in this trajectory, you can measure the time in this trajectory. If you are in this trajectory, you can measure the time in this trajectory. But these trajectories for the cosmological cases are megaparsecs apart, and we still cannot travel at megaparsec distances. So we cannot measure the time. The only thing that you can measure is the redshift. So let's try to do one clever trick where I have dt in the numerator, I divide it by dA, I'll multiply the entire thing by dA. Let's see what happens. So dt by dA in the numerator becomes a dA by dt in the denominator. So this dA by dt is a dot, this is just a dot times a. And I can divide this a dot by a, and this becomes a squared times a dot by a. But what is a dot by a? If you go back now, a dot by a, which is HA, is H naught times EA, where EA is the square root of this entire thing. So this I can now write in terms of EA. Which means that if I choose now A2 as A at T2 and A1 as A at T1, then I can change these limits also, which I should if I am integrating over T dA, which means this becomes, just writing it here, that A1 to A2, and let me just sanity purposes put primes inside the integrands. So that is the integral now in terms of A. So your homework is, write in terms of Z, redshift. Write this integral in terms of redshift. So that's your homework. That you can do by changing A to Z. And you know how A is related to Z. So once I have this, so that is this integral that we have evaluated. So I can now write the proper distance. So this proper distance may be calculated at the 2, so this is called T2. So this then will be, so the proper distance calculated at time 2 I can put the c by h naught outside, and then I get this integral. right? Aha, nice. Now we can ask the following question. What is the furthest in the universe that we can see? Can we see to the infinite distance in the universe? If there is a light ray coming from an infinite distance, can we see? Or the universe or this type of cosmology limits our observing universe to a certain limit. It is like when you are standing in a ground, you cannot see up to the edge or the entire earth just because the surface of the earth is curved. You can only see up to a distance. We call it the horizon, right? So we also call the same this also we call by the same name. We call this as particle horizon. Okay, you can think of this is the universe or this is the horizon. All the things within this universe, all the particles within this universe can influence you, because this is the furthest from which the light will reach you, which means this is the furthest from any other particle also can reach you and influence you. How do I calculate that? Well, this is the proper distance to the furthest of the universe, right? Furthest, you can say this is the proper distance furthest in past. So let me call this way, and we are calculating the distance at present. So I can just use the above formula. The furthest in A that I can put in this formula is of course A equals to 0. And again we are assuming that exists. And the if for the present, if I calculate it, okay, so let me not do it for the present, let me do it from any. So you can just put it for the present whenever you wish, but let me do it the for any time. So any time we can ask this question, that what is the particle horizon at that time. So I integrate up to that time, and this remains the same. If this integral is finite, then there is a particle horizon that exists. If the integral is not finite, if it is infinite, that essentially means that you can see up to the infinite proper distance in the universe. Okay. So this is about the past. So what are the events in the past which can influence you at present? Let us ask the same question, but now for future. So what if we say wait for infinite time? What is the farthest to which we can send a signal? If we wait till infinite time, what is the farthest to which we can send a light signal? So how do I calculate that? So I do the same thing, not now for future. And you may be calculating it at any time in the universe, in the evolution of the universe. And I get the exact same integral, right? So that is how you calculate the proper distance anyway. But what will be the now? What will be the integral limit? Well, it starts from t, and you are waiting for infinite time, so this goes up to infinity. See, you may think that if I wait for infinite time, eventually, at that part of the universe, a signal that I send will reach. Eventually. But that may not be true. If this integral does not converge, then this of course is infinite. But if this integral converges, then if you even wait for infinite time, you take the time. The limit of the integral is infinity. Still, dp will remain finite. So we'll always be able to influence the finite part of the universe. Well, these things are not what we think using our common sense, but this is what happens for an expanding universe model, particularly as we have seen here for the Big Bang model. So I'll stop today's discussion here. I hope that you have come to this part, up to this part. Let me just go through what we have learned today. We started with these basic equations of the cosmology, and then we looked at the different types of universes or the universe model with only one type of matter, and we explicitly worked out what is the case for the radiation, and then made this table where I gave you the result for the matter and the cosmological constant. Then we try to plot the variation of density with the scale factor with our knowledge of the present day value of the densities, which comes from the omega parameters that we have already stated. And we realized that the universe initially was dominated by the radiation, then it got dominated by the matter, and then right now it is cosmological constant dominated. Then we try to plot how the universe was in early stages, as how the A evolves as a function of T, and we came to the conclusion that there was a very, very, very dense and stage of the universe, and at that stage also that the proper distance between any 2 points was small. So we made this statement that it is clear that there was a time in the early universe when the proper distance between 2 points having unit distances was very low at the atomic, of the order of the atomic scale or lower, and at that scale the classical theory fails. Our universe model which we are discussing fails, which essentially means that in this shaded region of this plot, or the shaded region of this plot which is sufficiently early in time, this model doesn't work. And as this model doesn't work, our earlier assumption that at a equals to 0, t equals to 0, or vice versa, t equals to 0, a equals to 0, we can go up to that time. So we cannot say what happened to our universe at a very distant past beyond this particular time. So we cannot say that the universe started with a Big Bang, etc., where a equals to 0. And that statement, and that is what I said, should be in your mind, and you should explain every person who tells you that the universe started with a Big Bang. That is the result of Big Bang model, because that's a completely wrong statement. The Big Bang model cannot tell you that the universe started with the Big Bang. We said where these confusions arise from. The confusion arises from the fact that often you use this model, assume it to be true at t equals to 0, and then try to calculate things. And we also said that those calculations, the values that we get out of those calculations are not always very wrong. They may be quite right, with the assumptions that t equals to, that sum of the limits goes from t equals to 0. But nevertheless, this model doesn't have t equals to 0. So next we first calculated the age of the universe, and to do that we first introduced, for the next part of the discussions, we introduced this function e of a, which is defined over here, and we wrote this age of a in terms of e of a, and then calculated the age of the universe, which goes inversely as 1 by h naught and depends on the all the omega parameters through ea. And we said that the present accepted value is around 13.7 billion years. Then we calculated the proper distance between any 2 points. From one the light starts and the other the light is received at time t1 and t2, and we found a formula for the proper distance, and we asked you to calculate the same formula in terms of redshift, which is the observable, and so that gives you the formula for the proper distance between any 2 points, two such points. And then we ask the question that is it that we can see up to the we can see light or anything from the furthest of the universe. Then the furthest is it that we can see up to things coming from the infinite distance in the universe? And the answer is there in this integral, which gives you what we call the particle horizon. And if the integral converges, then the particle horizon is finite. We can only see up to a furthest distance in the universe, finite furthest distance in the universe. Otherwise, it can be infinite. If it is infinite, we can see up to infinite distance. Similarly, so this was a question of the past because we can only see things in the past. So we asked the opposite question: can we influence things or send signal to the infinite distance in the universe if we wait even for infinite time? The answer again came out to be similar, that if this integral converges, then we cannot send up to infinite distances, we can only send to a particle to a finite distance, which is another horizon. And if the integral diverges, then obviously we can send distance, or we can send signal to infinite distance.